Oh, hello everyone. Thank you for being here. My name is Diogo. Thank you for presenting me. Work is neural networks for defect detection on eddy-currents-based non-destructive testing. And since this is kind of a generic session, I'm sorry if I explain something that you already know, or if I don't explain something that is not clear to everyone in advance. So the presentation will have this outline and motivation. How do we do magnetoresistive-based non-destructive testing, in this case, the current one? Our ASIC and the probe designs that we published previously, that was the base for this work, and the test setup that we used to do the experiments time and time again, the neural networks that was used, and the data set creation strategy, and the results and the people. So first of all, what is non-destructive testing? I think almost everyone here presented some sort of non-destructive testing. So we want to analyze a material, a product, or a base material, or end product, or something that is working. We want to understand its internal capacities, intrinsic characteristics, or external, because of some of the presentations here. And you want to do it without interfering with the materials, the intrinsic characteristics, or with the functioning of whatever is being used. It's very important for several applications. In this case, it was for aviation and nuclear energy residue storage. So you want to detect defects. And in this area, one thing that we are always striving for is which is the smallest defect we can detect and the deepest. And the deepest one. Actually, not everyone, and I have a not so fun fact to tell you in the end, if I remember, that will make you slightly uncomfortable traveling home by plane. But for this work, I wanted to know what was the smallest defect and the deepest defect. And how do we detect the defects in conductive materials here, which is necessary for eddy currents? So we have a primary magnetic field that is put in proximity to the material under test. It will create eddy currents surrounding this, circling the magnetic field. And if you have a defect, either it's a borehole or a line, currents will have to travel around it. And these currents also produce a secondary magnetic field that you can detect with, in this case, magnetoresistive sensors. To do the detection, so we fabricated the sensors. In this case, they are TMR sensors, so magnetic tunnel junctions, and we use application-specific integrated circuits. This was already published previously, but basically its necessity comes from the fact that sometimes, or many times, the primary magnetic field gets coupled to the PCB. If you have a very high frequency, not very high frequency, certain high frequency coupled to the lines, and so you get interferences in the field you're measuring and the field you're emitting. If you do the amplification, multiplexing very close to the sensors, you have less area for this coupling to occur. And in our case, the ASIC was capable of interfacing up to 32 sensors, and has an output of 4 to 1, so 1 of 4 in 4 of the blocks, and it has a gain of up to 40 dBs. This is the testing equipment. So we have a mockup here. Basically, in this case, it's an aluminum board. Then we have the PCB with the probe that I'll show in detail a little bit later in the next slide. We have a graphical user interface and the acquisition board. So this was done by several people. The probe is actually looks like this without its casing. So this is just the open version with the PCB for interfacing electronics. But the sensors and the coils here. You can see the excitation coil is a little larger than the sensor, which in this case are just this area. And the sensor in this case was a series of magnetoresistors, in this 72, with around 20 kilo ohms of resistance. And magnetoresistive sensors, they basically have a lower limit of resistance and a higher limit of resistance, and then a linear curve that depends on magnetic field. Now, related to the proposed work, well, we wanted to find these defects in the materials, so we need to define what is the pattern that these defects create. We need to create a data set, train the neural network, and then use it for pattern inference. And this is already kind of a spoiler, but this is the result of the analysis. So when you scan, like in a Z fashion, the material, in this case, it has some boreholes that go from 100 micrometers to 500 micrometers in diameter, and the depth at which they are from the distance from the surface is 100 micrometers to 500 micrometers also. We are analyzing on the surface that does not have the hole, so we actually want to find buried defects. And what you get is this type of Gaussian monocycle pattern. And since I'm a basic designer, so at some point I wanted to detect this pattern, and I was using thresholds, and its thresholds are okay if you are here, more or less okay if you are here, not okay if you are here. I also didn't want to go into all the already established algorithms that are in non-destructive testing that usually used 2D signals. I wanted to analyze the 1D signal. And you can see clearly that this is relatively easy to detect, not so much. And here, where we know there is a defect, but it's practically impossible to see. So this would be if you analyze the problem as a binary classification, this would be class 1, what we want to find, and noise would be class 2. So in this case, it's magnetic noise, the domains of the materials that are not perfectly homogeneous. You get this kind of signal that you see in here. So we want to see this, and ideally we wanted to stretch it to be able to see beyond what would be visual. So this is very simple, but in this case, the INN will correlate all the inputs and try to see how they match with the output that we have. As I said, we divided this in a binary classification. The neural network is a straightforward neural network with 200 input neurons and 50 neurons in the hidden layer. Now I needed to create all of these data sets, and in these mechanical experiments, as most of my colleagues showed here, you have limited data. You are not going to do 10,000 experiments. Well, maybe you can, but it takes a lot of time. If you're just one, you don't want to be in the lab doing 10,000 experiments. So I tried to see with simulation data this could work or not. So basically, I designed in console the board, or my team designed in console the board, the test board. We drilled the holes and we simulated the data. Now, this only has, if you notice, only has positioning and amplitude, already considering the gain and everything from the ASIC. And to get this into real signals, we need, of course, to change the height at which you're measuring, the depth of the material, of the defect, and then you also need to introduce noise. Otherwise, it would just not work. And aside from noise, if you want to go from samples or distance to time, which is actually what we are measuring, we are moving, and we are moving forward, and time passes, and you have a certain sampling rate. You also have to get these same results, and you have to kind of shrink them and amplify them so that to the neural network it's indifferent if it's the same depth or same defect. It's indifferent if you're moving fast or slow. And this is one of the simulation results, and what we did was get a real signal and then just add noise until the SNR is minus 18 dB. And well, the thresholds that we were using obviously fails when the SNR is close to 0. If you are experienced in looking at these types of signals, you can almost all the time detect the defects even close to 0 dB. The INN reliably, like I define reliably, like 50% of the time it says the defect is there, and it never says it's there when it isn't. So that's what I define as reliable. It's better than just guessing. With minus 18, which was not something that I expected, so it was a very positive result. So how does the INN analyze the data? As I said, I wanted to look just at the 1D lines, and I move basically the inputs from left to right in a sliding window, and then we get which looks like this. So if this is the worst one with more noise, and every time it goes to 1, it's basically the model indicating the probability close to 1 of having a defect there. So the smallest, deepest one that we detected was obviously the one that we had available. And in the end, the 2D scan looks something like this, which makes it much easier for automated detection algorithms now in image processing that are available everywhere to detect this. Okay, yeah. One interesting fact is that this pattern happens everywhere. So actually the neural network that I told you I trained for this was not trained for this application. It was trained for detection of dipoles with this type of sensor. So I just had to do some variation in training data, so make it larger or lower or smaller to get these results, which was also interesting. Another interesting fact is that the input layer is 200 neurons, and I only had 200 samples from the beginning to the end. So I also had to interpolate the signals and create data that was not there, and still the neural network behaved well. This also means that I could have a neural network probably with just 15 neurons to make it much simpler, because there was no data in the interpolated data. And that's something that I will probably do in the future. The not so fun fact that I wanted to tell you is that when I presented these types of results, meaning that we can detect 100 micrometer defects at 500 micrometers of depth, to actual air companies saying that this is great, you can detect defects in plane wings much earlier, you can do whatever you do to fix them, they just tell me that they're not interested in this, because this is too fine, and if the plane crashes and you did detect this, then you are liable. But if you just detect the 1 millimeter diameter, which is in the regulations, and you don't detect this, you are not liable. So they are not interested in detecting such small defects, which is a little bit worrisome. In conclusion, we used an ASIC to interface the MR sensors. This was previous work. We created the data set just based on simulation, and it translates very well to real data. To extrapolate, to increase the data set, we did some linear transformations that do not add any information, and we were able to detect reliably negative. So for future work, I'll have to check if this also works with different types of defects. So these were boreholes, and also develop an automated method. Thank you for your attention.